Hello, everyone. I'm Jamie Peterson, Director of WolframU. 2 weeks ago, we launched version 15 of Wolfram Language and Mathematica, and today we continue with our new in version 15 webinar series. Today's session is dedicated to the changes for TimeSeries based on the tabular framework that was introduced in 14.2 and new ModelFit functionality. Joining us today are Wolfram developers Gosha Konverska, Rob Knapp, and Giulio Alessandrini. You'll want to read Stephen Wolfram's release announcement for his comprehensive coverage of the new version 15 functionality and his philosophy for applying computation in the world of AI. We'll share the link to his blog with you. Also, to try the examples from today's presentations, you'll want to access version 15. And we have a free trial offer, so you can get started with that right away. I'm going to ask a poll question to the webinar audience now about whether you've already upgraded to version 15. We have a YouTube live stream audience as well, and for those of you on YouTube, please feel free to type your responses, comments, and questions in the chat. We have Wolfram webinar and technical staff joining during the live stream to help us coordinate Q&A, so I encourage you to type your questions as we go along. Our staff will answer what we can in typed responses to you, and our presenters will have a few minutes to address remaining questions at the end of each of their presentations. Let's take a look at that poll question. Wow, that's amazing. I don't think I've ever seen 100%. We'll leave that poll open in case there's a few more people who want to respond there, but that's fantastic. Everybody has access to the latest technology in the new version, and a few a few stragglers, which is kind of what you'd expect. But let me point out a couple things in the webinar interface before I go. The chat and Q&A area on the right of the screen is where you can submit questions as we go along, and where you can read the published Q&A. A download link with the webinar presentation notebooks appears in the pinned note at the top of the chat panel. So go ahead and download those notebooks so you have those as a reference for you later on. Finally, make note of the full screen toggle available in the top right corner of the presentation window. That will help your experience if you're finding things hard to read on that screen. We'll be making new notebooks available each week as we continue the series, and we hope you'll plan to join us at the upcoming new in version 15 webinars. So that's all for me. Thanks for your attention. Without further delay, we'll get things started with Gosha to begin today's presentations.
Yes, so hello everyone. My name is Gosia Konverska. I work as a kernel developer in the area of probability and statistics. And I'm going to be talking today about what we call TimeSeries Event Series 2.0, so the new version of the time and event series based on the tabular framework. I'm going to now focus on the notebook. And here, okay. Oh, great. To see the sample results. Okay, so I see some people familiar, some people not familiar. So I'm going to see the simple examples for those who are not familiar with time series, event series, and some of the new facts will be very useful, I think, for the current users. So as we mentioned, the internal structure for the time series and event series is now based on the tabular framework. That means that it's based on the tabular and tabular column structures. By popular demand, the time series and event series now have their own heads. So that's, I think it's a big change, especially for those checking, whether that was a tabular data with the, time series color or not, and will require, looking, how you check for your objects. So this is a time series, event series proper, and they are atomic, so they're atom Q. And it means that we can extract the parts in the sense, of the parts of the path, really, and then that's with the double, bracket here, and then extracting with the single bracket gives you the value at the given timestamp. So this is as it was. And what is very nice right now is that the time series event series can store calendar timestamps with all the information, and that includes granularity. So you can see that we can have the calendar timestamps with the day granularity. And what is here? It's just a simple definition of a time series. We have some new properties that might be sprinkled through the talk, but one of them is timestamps, and that's going to return the new format, in which the timestamps are being stored. And this is going to be returning a tabular column and of whatever it is, whether our times were integers or whether real or our calendar, it's going to be always a tabular column. And every tabular column will have a type, so the element type. And here in this element type, we have all the information pertaining to the calendar information. So this is the day granularity Gregorian calendar, and we have no time zone specified. Right? And normal gives us just the the dates. So this is the normal of this tabular column that gives us the list of the dates. Okay, what are the improvements to time series? Some of these features here will also apply to event series, but I think they're mostly important and mostly applicable for the time series. And I start here with, again, a very simple time series. Values are 1 to 3, and the time's gonna be automatic starting at the value 11. And we have a slightly improved summary box that gives you the length, which is the number of elements in the time series, but also a duration of the, that's based on the times in the time series. And what we can do, we have, when you expand this summary box, we have a little button, it's preview, and it kind of shows you a little preview of what the time series, what the data is inside. Now, we added a new free argument syntax that allows to input the keys for the value components. So with the tabular framework, we can have keys for columns, and in similar fashion, we're going to have here keys for the components of the time series. And when we have this time series with the components, then they will be included in this summary box, and the preview will basically show you the column with the given key. Okay, there is a difference between having a simple time series with no components and time series with the name components. Basically, you can compare the normalizations. What we get in the normal version of the simple time series, it's just a list of time value pairs, and this agrees what I'm going to be referring to the legacy time series, so the pre 15.0. But in the presence of the keys for the components, the result here, the values are given as associations. And also, there is a difference in the structure of the values. So the values of the simple time series are given as a tabular column. We have no keys, so there is no need for the tabular. And then values of the time series with the named components will be given as a tabular. And then here we have the column with the appropriate key. We can, of course, have many components. This is having 100. And one of the new properties here is the component keys, so to list all the component keys for the values. And then we could convert this time series to tabular. And you can then display and just investigate. Oh, sorry. Investigate of what's happening in this data, basically. Now, similarly, like in the tabular, we can use extended key, and this allows to create layers in the component keys. So what I have here is the temperature and air pressure readings for 2 cities, Chicago and Denver. And you can see that asking weather data for a given property within the dates returns already the time series. So we have a time series of temperatures and a time series of air pressures. What I'm going to do is to get all the dates. So so our time series have the same amount of timestamps, and I'm gonna then ask for the values at these dates. So we have the same length of the values. And so what we can do, we can group this by city. So I will have the temperature pressure for the Chicago and temperature pressure for Denver, and create the time series with these new keys, the extended keys. And what it does is basically gives us this layers here. So I have a Chicago temperature and pressure, Denver temperature and pressure, and then we can of course do it the other way and group by property, again using the extended key. And then our tabular looks really different because it's a temperature for each city and the pressure for each city. So that gives us the way to visualize data depending on the what we want to highlight, whether we look at the temperatures or whether we look at the city properties. Okay, so now default keys versus no keys. So there are the situations where we have no keys, just as I showed before, the very simple time series. So what I want to start here is this data. This is very simple data, just a list of pairs of real numbers. But this is probably the most ambiguous data for the time series, because we can treat it as the time value pairs. So the first number, it's a time, and the second is the value, and just feed it directly to the time series. So time series of data. That creates just a single path of for the simple path time series. No components. When we do the normal, this agrees with the legacy behavior, and this is exactly as the sorted original data. This data can be also thought as a vector values. That means that we input data as a value argument, but then we have to add another argument for the times. So now we have a vector value time series, and when we normalize that, this again agrees with the legacy behavior. So we have a time value pairs as a normal, and we can see that when you look at the values of this time series, this is a tabular column, so the simple case, but we see here in the element type information that we have vectors of length 2 of real 64. So that gives you the information that we have, that our values are two-dimensional in this case. And then this 2D vectors can also be split into components, which gonna give us yet another incantation of the time series. So here I'm gonna use 3 argument time series, so values, time, and then the third argument, empty list, which requests basically creating a default keys for the time series. And so now I can ask for the column keys, and here we have the column keys on the corresponding tabular. So we have a timestamp for the times, and then the default keys for the value component. So component 1, component 2, and this component keys can also be specified using an option. So component keys on the list, and we have a component keys. Now things get slightly tricky here, because the timestamp key is fixed. So we cannot rename the time column. It's going to always be a timestamp. This is how we're going to refer to this. There is always one series of times in a time series, so there's only one timestamp column possible. And with the simple time series where we don't have components, we're going to have the key value as an implied to be used in some processing functions. So this is this is the example here. So we have a simple time series with the values 1 to 3, time starting at 11, and we have no components. So if you ask for the property on this time series component keys, it's going to tell you that there is none. So there are no components. Okay, but because we need to have the implied keys, because need to have keys in the tabular, when you ask for column keys of this time series, you're gonna get this list of 2 keys, because in the tabular, so after conversion of to tabular from this time series, we're gonna have these keys, and this is what we see here when we convert to tabular. Why we need this? We need this for the processing function. So right now, the because of this tight integration with the tabular processing functions like transform columns can work directly on the time series. And in this processing functions, in these transformations, we need to be able to refer to the columns using the keys, hence the need for the key. So for example, square all the values. That's a new transformation. That's a new time series with squared values. Okay. So we think about time series as some kind of a sampling of some kind of property changing in time, and so in a way can think about as some kind of a function of times, and so that requires that all the times, so the timestamps, must be unique. And when we convert to the tabular representation, they will constitute something which we call the key column, and that allows us to basically refer to the row using the elements in this key column. But this uniqueness is necessary for this for constituting the key column. So we have a new option kind of for the time series merging function that allows to specify how to treat the values with the identical timestamps. And there is some default behavior, and this is gonna depend on the type of the values. And if we can compute mean, meaning that the values are somewhat numeric or something that mean is meaningful, that's gonna be the default behavior. So this is the time series of numbers 2, 5, 6, 9 with times where time 11 is repeated. And we see that when I create the time series, now I don't have a 4 elements, but 3, and each time is unique. And the value here, it's the mean of of these 2 elements. For the non-numeric types, the default merging behavior is to keep the first value. So these are some symbolic elements. It could be strings, for example, and we're just gonna keep the first value. And we can specify different behavior. It could be, function total, so we get the sum of the elements from the duplicate timestamps, or anything else, I would say, that would make sense for your values. Okay, and clearly, if you can put any function, it may just kind of return nonsense. But as you can see here, we can have colors as the values, so we can really have any object as the values in the time series, and then merging function makes sense for the colors. We can do blending of the colors from the duplicate timestamps and get a valid time series. Okay, so I want to touch on the types. The types, is new in the time series because this is a feature of the tabular framework. So we're gonna have the types, specifications in the values of the time series, and this, as we saw in the merging of the duplicates, the types will dictate what's the default behavior, and this also will dictate how the resampling, what is the resampling method, by default. So if we have here numeric inputs, and so this is a time series again, 2, 5, 6, 9, but I have now here all the times are different, and I ask for the value at 12, the time 12, which was not an existing timestamp. It's gonna give the linear interpolation, between the values here, and you can access can query the component types and the resampling method by the properties. So this is the integer 64 now, and then the resampling method linear interpolation. For other types, right, we would by default have a different method because it doesn't make sense to interpolate strings, for example, and the default is to hold the previous value. So we see here that the value of this time series at 12 is the A, and the value at 13.5 is B, string B. And again, querying, you see that our type is string and the resampling method is previous element. And we also have a new method for resampling, which is to use the nearest element. So Again, so 11.4 gives us A, and 12.8, which is very close, to 13, gives us B. We can also use the column types, the function from the tabular framework, to get the types for the corresponding tabular object, and that would give us also the type of the timestamp column. And just a side note here that we cannot really resample on a tabular object. So even though we kind of think that tabular and time series are very close to each other, we cannot really do this resampling. This is not the operation defined here, because if I want to access something which is between 11 and 12, this key does not exist. So there is no row corresponding to the row key 12. But what we can do is to convert to the time series and then resample using some resampling method, and then convert back to tabular. And now we have here a row with the row key 12 and new value, and then we can query this tabular at this row key of 12, and then we get here the values from the row. Okay. Now for the event series, we want to think about event series strictly as a series of events, of temporal events, and in that sense, we will allow duplicate events in the event series. So we're going to have duplicate timestamps. So I have yesterday A, yesterday B. When I do create the event series, you see that I still keep the length 4. So I have 4 elements in the event series. And when we do the normal, you see that the duplicate timestamps are being, retained here. And the difference is that because we do not guarantee the uniqueness of the timestamps, the corresponding tabular doesn't have the key column. So the timestamp column is not a key column. And you can see that when you look at the output of the tabular, we have the index column here for in front of the timestamp, and the timestamp is just a regular column in this tabular. We can also merge this in the event series. But it's just not done by default. So we can use the merging function upon creation, say string join for the strings. And when we extract the value, it will return a single element, the first. We can also merge the duplicate events, the values, upon extraction. So this is querying event series on this timestamp and then asking for the merging function. So just for this instance. And you can also ask for all the values at the given timestamp. The other new feature is that we can have just the temporal events. So we can have just the times and have no annotations, no values, which in this case is specified by the empty association, and then provide the list of the times. This is how the normal looks like. So there are no values. So we have some indication of, something empty here. And asking for the values gives us an empty tabular. It will still gives you, the row count. That's how many we have. And then corresponding tabular is just a single column of the timestamps. And you can, use this event series directly in some visualization functions that will just show the temporal events, like the timeline plot. Okay. And then as before, the event series does not admit resampling. So basically, yes, there is nothing between the events. And if I have here event series with, this times, and I ask for what's the value at time 1.5, I'm gonna get missing because there is nothing, and there is no event with this time. And since it might be difficult to know the exact time of the events, we have the new extraction functionality that can give you all the values within given a time interval. So if I query the event series at the interval, you're gonna get the tabular column of all the values within this interval, and normalize and get the list of them. And this also works for the calendar times with date interval. So here's the event series with dates, and we can have event series querying over the date interval. It gives again the tabular column, and we can also ask for a different granularity, and it's gonna be respected in the sense that it's gonna find the appropriate times appropriate events within this date interval. And I want to close with kind of remark that there is a lot of connections between the time series and event series, and especially in the data. And I want to just kind of show you the code to reproduce the front page visualization. For the time series, this is a sampling of a distance between Moon and Earth over some range of dates. So this is our time series. And for the event series, we have the events of the full moon, so the dates of the full moon. And coordinates here to plot, this is basically at each date of the full moon, what was the distance of the moon from the Earth. And then we can plot this. And what it tells us is that right now we are here in July, and during the full moon phase, moon is far away, so it does not appear to be large. And then you see that when we get back to winter, we're gonna see that this full moon is gonna be like huge, relatively. It will appear just simply very large. So this tells us something about, what we can see on the sky. Okay, so thank you, and I'll look into questions if there is something that I can answer here. So
Thanks to Rob, who's been busy answering some questions. You can see some of his answered questions. We have a couple open questions still there.
okay, so there's a question here about having data from several measuring devices, and each of them kind of has a maybe different set of the timestamps. And if you want to use time series, all this has to kind of be, I don't know how to put it, coerced to a single collection of the timestamps, because time series only allows you to have a single timestamp information. So what I think it's a good idea is to use your original information, right? So you can create individual time series for each of your measurements, and then just simply what I did for the weather data in between the cities, find the union, if you want, of all the timestamps from all your devices, then find the interpolation, so resample basically each of the time series on this union of the timestamps, and then you can create a single time series with this union of the timestamps, and then you're going to make sure that you have the matching, everything it's matching because it's a single timestamp column in a way, and also know that you used all the information for all the measurements as truthfully as possible, because in each scenario you could possibly have a different resampling method. What I didn't say here is that when we have a time series with, a single time series with multiple components, you can specify a resampling method for each component separately. Just basically give an association with the keys and then specify the resampling method for each component, which is I think needed when we have components of different types. Okay, so there's a question: how is temporal data object affected by the changes? So temporal data at the moment stays as is. So nothing changed in the temporal data. Maybe some conversions between temporal data to the new time series, event series objects, and vice versa. But all the functionality with the temporal data is the same. So if something is, if you still would like to work in the old framework, you could use that. You can use temporal data, and you can specify a resampling method to be the interpolation of order 1 to resemble the time series behavior. And we will be thinking about, kind of upgrading the temporal data object, in the future. But at the moment, this behaves in the same way. I'm not sure that I understand the other questions, so I'm sorry. And I think I'm just gonna close my part here and pass to Rob Knapp, and I will stop sharing. Thank you.
Hi, my name is Rob Knapp, and I'm going to present to you today about TimeSeries and Tabular. So Tabular is a column-oriented data frame. It was introduced in Wolfram Language version 14.2, and it has a number of other advantages over ways of representing data, like lists or data set, including the following. So storage is compact, so overall memory requirements are much less than say, data set. Operations on columns are often type targeted for high performance. So each column has a particular type, and knowing that type can mean we can do very fast operations on those when the types match. The display is very readable and only views a part of the data, even from millions of rows, so you don't end up getting too much stuff in your notebook. And there are also some really efficient methods for importing and exporting from files to Tabular and vice versa. So for version 15, we decided to restructure time series and event series to use the same column-oriented data structure as Tabular. So this means a whole bunch of stuff, but some particular highlights are the conversion from time series to Tabular shares the column memory, and it takes essentially no time. That means you can go back and forth with pretty much seamlessly. And a particular advantage of this, that means that most functions we designed for Tabular, like transform columns, aggregate rows, construct columns, select, so on and so forth, can be used directly on time series. And they'll typically return a time series back. And also, another big thing is timestamps are now stored with a tabular column date type. And that means that date computations are somewhat faster and sometimes by orders of magnitude. And also dates now come with the granularity. Before they were just stored with an instant granularity, but now you can specify the granularity, which is much more consistent with our date object arithmetic. So to show you the effects of these changes, rather than go into details in them, I'm just going to show you a couple of relatively simple examples that should illustrate some of the ideas that relate time series and tabular. So let's consider days since the millennium. Okay, and so here what I've done, I've constructed an event series, and in this case, this means that each event has no value associated with it. Okay, so these are just events without particular values. And there's been almost 10,000 days since the turn of the millennium. It tells you that. Another thing you can look at is you can add the plus, and it tells you things about the duration, but you can do a preview. And that preview is actually a tabular view into that. And you notice you can actually scroll that preview. I know this is not very exciting because we're just have a bunch of dates, but that's but we're going to eventually do something with those to make it a bit more interesting. So the storage is quite compact. So the byte count is basically 4 bytes per entry. And forming a tabular from this essentially takes no time. So we could do repeated timing on this, and then we get that same tabular we saw in the preview. But notice this takes on the order of, less than 10 to the minus fifth second. So it's very, very fast. So and again, it's sharing the memory. So we're not using any extra memory to do this whatsoever. Okay, so let's do some things with the list of days. So a thing you can do now that's quite easy is you can use select, which wasn't possible before on time series. And this basically uses the tabular select to do what we want. So the date value, remember that column was called timestamp, and it will always be called timestamp in time or event series. Okay, so I want the day to be 13, and I want the day name initial, and I chose that to be F for Friday. So I can do that, and that's super fast. And compare this to doing it with the normal version of it. So I could get the normal of days, and that'll be the days as date objects. And then I could do select on the day list with basically the same function, except it's just a simple hash instead of a hash timestamp, because there's only one element in each of the lists. I can do that. And now this takes roughly 160 times as long as the version from the direct time series using the tabular data. So that's an example of date computations that are super fast now. Okay, and then we can also enhance things with the properties of days to make it more interesting. So what we're going to do is we're going to take that days, which is just the days and no values. We're going to use, treat it like a tabular. Think of it as a tabular with just one column. And we're going to enhance it by doing this. So in transform columns, when I put a column name that doesn't already exist, it creates a new column based on operating this function on the current columns. So in this case, it's going to take the timestamp, it's going to give the day name short, and so on and so forth. So I can run that, and I get a new event series. Okay, and to see what it looks like, I could look at the preview, but to make it easier to see in this notebook, I'll go ahead and do that. So now I have columns, the original column of timestamps, but now I have day name, whether it's a business day or whether it's a holiday. Now, because we can think of this as a tabular, as shown here, you can think about doing sort of operations for data aggregations or manipulations of the data that you would do for sort of a table of data. And one of those is pivot table. So what I'll do is I'll take that tabular above, I'll consider the number of days, which is basically given by this length. Okay, I'm going to group by business day and holiday and day name, and I'll show these on the vertical axis, and I'll show this on the horizontal axis. So when I do that, here I get a summary of days based on the type of day and whether it's a classification of business day and holiday. So what's interesting here is you can see that the only cases that are neither business days or holidays are the weekends. So you can see, and also you can see that the most common holiday, i.e. that's not a business day, is Monday, followed by Thursday, and of course Thursday because of Thanksgiving. So all right, so now you can also do aggregation. So here's an aggregation by years of this. So I've taken what I've done is I've tried to figure out the number of holidays in each of the years since the millennium. So what the bool, so holiday is true or false, bool of that converts true or false to 1 and 0, and then I take the total of that, so that gives me the total number of holidays. And again, I'm grouping the second argument. The third argument here is what I'm going to group by, and that's going to be the year. And again, I'm just going to use the date value of timestamp year. So here I get a number of things. And I could, for example, then do sort by %9, comma. Suppose I wanted to order the years by which had the fewest or the most holidays. So I go from 5 all the way to 2021, which had 15 holidays. So it gives you a really quick way of looking at the data. And we can also, again, do the same sort of thing with this aggregation, but we can make a pivot table out of it, and that would give me something like this. So here we see year by year, where do the holidays fit in which days? So that's a quick summary of the data. So that's a very simple example. I think it shows, a bunch of things. It shows being able to add components or columns easily. It be able to show how to use transform columns and how to use aggregation functions like aggregate rows and pivot table, which are super useful. So another example, which is a little more sophisticated, is analysis of a bicycle ride GPS data that was collected several years ago. So rather than show you how to import it, I'm just pulling it in as a time series. It sits in this notebook. And again, I can look at that preview, and this might be hard for you to see, but there's a timestamp, a track, and an elevation. And we can, again, look at a good way that I often use to look is just do the column types to see what the column types are. The timestamp, which are dates, the track, which is a geoposition vector, and then the elevation, which is in meters. Another nice way to do it is to do time series summary of ride data, and this shows the data in sort of a summary form that's easy to read. So you can see the column names and then some properties about the columns here. So let's start to do some more analysis on this. So first what I'm going to do is I'm going to take out the track column, which I can convert to tabular, and then all of track. That's how you can get a column out of these quite easily. Okay, and then I'm going to convert this to a single geoposition, which is just done by wrapping geoposition around the track column. And geoposition columns have a certain amount of functionality, but geoposition itself has the most robust functionality within the whole Wolfram language system. I've also imported a position of the continental divide, the U.S. continental divide. And here's a map shown of my here. Yes, okay. It took a little while to come up, but this shows my track with the continental divide. Now, the continental divide track from this file is quite approximate, so it doesn't really follow. It's got relatively few points for the thousands of miles that it actually goes up the continental divide, whereas the track is lots of points here. So it appears that it crosses it many times. That may or may not be correct, but at least it gives you an idea that part of this ride was right along or very near the continental divide of the United States. So the GPS data is not very accurate for position and for elevation. It's quite accurate for position, but not so much for elevation. So we can use the built-in geo-elevation data in Wolfram language to get corrected elevation. So once we have this geoposition track thing, we can just do geo-elevations. That gets the geo-elevation data of the track. Okay, and this takes a little while because it has to go to a database and collect it. But it doesn't take terribly long. And then what I can do is I can use insert columns. So this is, rather than using transform column to make new columns, I can just insert. So this is an existing column. So I'll just insert that in here. And there we get it. But frustrating. Look at this, the units are different. So it's very hard to look at them and compare. Well, again, that's fixed by a simple transformation, which I can do unit convert elevation to feet. And since I'm an American, I read things easier in feet than meters. And so now I have the elevation in feet, and then we can visualize the elevation and see what it actually looks like here. So that's quite nice. And there are gaps, and that's because there's gaps in the timestamp where we were resting. So they look, on the whole, they look fairly close, but realize this is over a couple of thousand feet is the vertical scale. So if we look at the difference, okay, how much was it corrected? In some cases, it was corrected by quite a bit, up to more than 100 feet in some cases. And in many cases, as much as 50 feet. So we may want to use the corrected elevation versus the actual, the GPS elevation that the GPS device itself collected. And particularly probably these biggest deviations are where there was fairly heavy tree cover and the GPS doesn't do quite as well. But let's go further with the elevation data, and I'll just use the elevation data for now. The GPS elevation data for now, but let's look at how can we smooth that curve a bit? Because if you look at that curve in the back, it's very rough. There's lots of little mini peaks and valleys. So the idea is we want to find where the bigger climbs are and the low points are. So what I'm going to do is I'm going to use a scale, which is the quantity of 5 minutes, and then I'm going to find the highest points and the lowest points based on that scale. And this is a new version command in version 15. This is called TimeSeries events. So, and it will find so what this does is it'll use a time series, and you give the column you want to consider, and it'll find local maximum. It'll also find zero crossings as well if you ask for zero crossings on a time scale. Okay, so I run these, and then I can do this dateless plot, and you'll see it's getting the bigger peaks and the bigger valleys. But it sort of it skips stuff like this because that's on that time scale, that's not a significant peak or valley. So this is a very convenient thing to get, to get the bigger trends, and super useful for like stock prices and stuff like that. So let's go and do a bit more analysis, and let's find, so far all I have is elevation and the geo elevation. But what I want to do is I want to know, well, what was the overall distance? What's the cumulative distance and stuff like that. So I can compute the distance by using that I'm using that geoposition track. So I use this geodistance list. I'll convert the to miles because, again, I'm American. I tend to think things in miles. And because this is like differences, it gives one less than the length of the track. Well, to fit it into the table, I need to pad by an extra amount of quantity. So I'll just pad by 0 miles at the end. And again, to get the differences in time, differences gives me something shorter. So again, I'll pad, in this case, I'll pad with missing, which fits perfectly well in this. And now I've got the new tabular where I've added a bunch of columns. So I've again used insert columns. Okay. And now I've got a time interval for between each timestamp. I have a speed between two timestamps. I have a local distance. So this is a distance traveled between two timestamps. And of course, a very interesting thing is the cumulative distance, which I calculated by doing it. So I added these columns, and then I calculated the cumulative difference using the column-wise thread of accumulate. So this allows us to get a column-wise thing in the value. So here we can look and see eventually the whole cumulative distance was 42 miles. So I think that adds a lot of utility to the table to have that extra information, which of course is lying in the original 3 columns of information, but it's nice to enhance it. And that's something the tabular form allows you to do quite easily. Okay, so again, we can plot the speed as a function of time. Okay, and this is very typical of GPS data used to compute the speed. It's super rough. I mean, it's really, really hard to see what the actual speed is. So a useful thing to do is to smooth it a bit. And the time series functionality it's always had this, but this moving map function has been enhanced to work with a tabular form, and often quite efficiently. So I can make a smooth. So if I smooth over a quantity of 1 minute, it'll be a little bit smoother. And if I do it over 15 minutes, it'll be even smoother yet. And so you can actually see that the orange one is the smoothest one. And that may be too much smoothing because it probably has, cut out some points where the speed really was quite a bit higher than this. Say going down a hill or something like that. So we can do, what I'm going to do is I'm going to do a similar computation here. I'm going to take a scale of 100 hours, but moving map also has now the ability to make a time series with columns. So I can make a moving map of the mean of speed. So I've got that speed column. I can take the mean of that. Okay. And that what it's going to be doing is going to be computing the mean of speed over each quarter hour. And it's going to show that versus the average speed. And the average speed is actually different than the mean of speed because it's the distance traveled in a given amount of time. So for each 15 minutes, how far did I actually travel? So we can run that moving map. And you notice this has created a time series with timestamps, but it's now, if I look at the preview, you see you've got two columns, one the mean of speed and the other. And so I can plot those and it automatically plots both things. And this is the actual average speed is the gold versus the mean of speed. And it's always going to be a bit lower. Now, one of the reasons it's a bit lower is because that's just the nature of the average speed versus the mean of speed, but also because the average speed does include resting time. So these points where the average speed was relatively low are points at which I was resting. So we can actually, so a question is, well, how do we classify? So what I've chosen a threshold, say if it's moving less than 0.5 miles per hour, the GPS kind of wanders even when it's still sometimes. So I'd have to choose a threshold. And if it's greater than that, I consider to be moving and otherwise it's resting. And so here we can classify the moving time versus the resting time that way. And then we could select in the timestamps and filter the speeds by that. I'm not going to do that because I just don't have time to go through all that. But I think that gives you some example of sort of the analysis you can do with our framework on different sort of data. Okay, so in summary, time series and event series have been restructured to take advantage of the tabular framework. Okay, and some of the things I'll emphasize that I showed is conversion from time series to and from tabular is seamless and essentially instantaneous. And data components or tabular columns can easily be inserted and created. And data transformations are really natural using transform columns. The data visualization uses a syntax similar to tabular with the natural handling of timestamps. The general data filtering can be done super efficiently with select. Data aggregation can be used on the tabular form, as I've shown a few examples. And the data smoothing can be done using multiple components at a time. So there's a lot more to time and event series, and I hope this inspires a deeper look into the documentation. Thank you very much.
Rob, were there any new questions you wanted to address? I know that we've done an impressive job keeping up with that.
Yeah, I didn't see any new questions yet, but I'm having trouble sharing my screen now with it's asking me if I want to add video or not.
Let's try that again.
Share, it's the share content button, right? Oh, there we go. Okay. So it was just coming up with the wrong thing. Okay. So from share. Okay, got it. So yeah, any other questions I'd be happy to try and answer. And if not,
I think that's a really good question about deciding between tabular and data set. Is that something you might want to just kind of speak to?
I could elaborate a bit on that more. Again, I tried to answer that. So data set is very, very general. Okay, so you can have unstructured things that are not rectangular, and data set sort of handles that in a way, and it has many can go down multiple levels. So if you've got data that's very multidimensional and sort of somewhat unstructured, that's probably the way to go. But if you've got data that can be expressed in 2D, as rectangular things, the tabular is going to be much more efficient. It's one, the memory can be, a factor of 10 or 20 lower for tabular. And also the speed of operations can be, say, 10 to 100 times faster in some cases, particularly for typed things. Okay, so I see there's a couple more questions now. So I'm going to scroll back to the beginning. Let's see. A histogram that wasn't in the distributed notebook. So yeah, that's this is this time series summary that I probably didn't. So is this what you're asking? Is the time series summary? So this is just this is just a quick summary of the time series, and there's something called time series summary that does. There's also a tabular summary that does a similar thing, and the histogram, may or may not be meaningful. In this case, I think the elevation histogram is kind of interesting, and the timestamp histogram is probably not so interesting. It sort of says it's hard to decipher information, but this is the summary commands are quite useful for these. And it gives you statistics about the things. And so that's yes. So and what about tools from dynamical systems for time series forecasting? That's we're going to be working on in future versions to make that more effective. And fairly soon there's going to be a financial package that's based on the new time series coming out that will do lots of forecasting and Monte Carlo simulations and things like that. And what's the easiest way to place graphics? Probably you can use row to place graphics callouts horizontally. And that's probably the easiest way. Or if you want a grid of graphs, you can use grid around the graphs. Use tabular with amongst. Well, that's that I think you should, that question about using buttons in tabular, and I can see why that could potentially be slow. That's probably a question to send to our quality assurance department or our technical support department, and they would be able to answer what possible things of that. What's happening is the front end has to sort of negotiate the button and the dynamic input with the button, and it's going to be very problematic with the scrolling, and I see that. But again, our step 4 support may have an answer for that one. Okay, so I think that's all the questions. It's probably time to move on to Julio. So I will hand the presentation over to him. Thank you.
Thanks, Rob. And we're pushing out a poll that Julio had wanted to ask. So we've got that poll on the screen now for you, Julio.
Testing for Julio. Can you hear us?
Yeah, look, I see your mic is on, Julio, but we're not hearing you. You might need to check the settings in that mic settings option, or even exit and come back in. I know you were trying to monitor a couple different things here. We'll let everyone get a chance to answer that poll question while we wait for Julio to turn his mic on.
Hello.
We can hear
I
you
hear
now,
you.
Julio.
Hey, okay, sorry. I don't know why my headset was kind of kicked out of the system. So well, thanks for the intro and thanks for the poll. I was trying to explain that so far in the Wolfram language we had like kind of two basic ways to do fitting. The workhorses, fit and find fit, that you might care about only if you're interested in like just a mean value of the equation itself. But if you want to do statistical inference, we have linear model fit, non-linear model fit, and friends that gives you this fitted model object, and you can query it for like properties AIC, BIC, R squared. I myself tend to use a bit of both, depending on what I have to do. But I see that more than half of the people here have used at least one or more of them in some capacity. Okay, why I'm asking this? Because what I'm going to show today is basically kind of the continuation of this. So I'm the team lead. I'm Giulio. I'm the team lead of a machine learning team at Wolfram. And so my goal for the past release and probably a couple more is to kind of revamp our fitting framework, our statistical inference framework. I can update all the functions and make it more modern, more modular, more pleasant to use. So I guess without further ado, if I can go back to the hi, that's me. So quick introduction, and I'm going to bring up the screen again. I hope you see the presentation. Okay, I'll keep my camera off for the presentation, so there's a bit more bandwidth. Let's start. Okay, so classic setup. Stopping distance, car different speeds, something that you measure. I'm going synthetic here, but in the documentation we added tons of examples with the kind of real data, which I hope can drive real applications. So this is standard formula. You have depends on the speed, on the speed square, and some random noise. I mean, this is what you get. I'm just initializing data here. This is a simple data set, but I'll carry this one through the whole presentation, so we don't get distracted by data variation. Now, how do you fit this? New framework, one-liner. ModelFit data model. This is the opposite of the old framework. The idea here is that you have a single function that is your entry point for fitting, and we'll kind of decide, you know, like what you want to fit, the data slicing, the properties you want to get out of the fit, and then each model is its own symbolic object with its own properties, its own hyperparameters that are tunable. Wherever the model is symbolic, you can always deal with it as an equation. So there's full transparency with the kind of its symbolic form. But you know, instead of concentrating on the fitters, we concentrate on the models. The model carries its own semantic, and each one of them will have like a rich documentation page and kind of guide you through how it can be used and when it should be used, what you can get out of it. So yeah, basic usage is just this. You pick a model and you fit it. So this is a polynomial of degree 2, as you can see here. What comes out of it is a polynomial model itself with values inside. So you see here, this new syntax tends to be very terse when it can. So in this case, you don't really care about dummy variables, and you didn't specify any parameter name. So we are doing this all automatically for you. And but of course, you can set your own names if you want. So the result is a callable function, and you can just run it. And you can put it, you know, in the new plot fit option, and you get the data in the fit. So you use like any other function, and if you want, you just use it, you know, on I don't know, S or V as we call the original one. Yeah, this is just a function. Now, so basically, the basic of the API is this one. Now let's see what more we can do with this. One of the benefits of separating the fitter from the models is that now you can pass more than one model and do model selection. So in this case, I'm passing a polynomial of degree 1, of degree 2, and of degree 3. And ModelFit is doing model selection for me and is returning the result. So in this case, it's picking polynomial model 2. What you're doing internally is that we train each candidate on different data folds. We compare the validation loss, out of sample loss, and pick the winner. And of course, at the end, we retrain the winner on the full data set. So in this case, 1 is not enough. 3 is discarded because being, going over with the degree is overfitting and has a slightly worse error out of sample, and 2 wins. We are working on kind of compact ways to specify whole model families. So in the end, you can you can fit polynomials from degree 0 to 6 just by doing this. And as people are asking me examples, so this, if you expand this basically becomes something like let's say so you want to test this. Oops. Okay. Oh yeah, because I didn't map it, of course. Sorry, I have a new keyboard. And there it is. So as you can see, this stuff can get very, very large, very, like you can write this stuff manually, but the interesting part of the kind of terse syntax of the framework is that this is a lot terser. And if you have 2 variables, for example, now this was the same, x and y is just a lot more difficult to write. If you don't care about it, you have 3 variables. You just say 3, and again, we have symbolic variables here, but like this saves you writing by specifying by hand parameters, like what is this 78 plus something, so it's 80 plus parameters. So how you do this fully symbolically, I'm going to show that later. So I hope I can answer that question later in the presentation, but otherwise we'll come back to it at the end. So why this thing works. So basically what we do inside by default is what is called k-fold cross-validation. And but any form of cross-validation we do is working the same way. We take your data, we split in a training set and a held out test set. We train on the training, and then we measure the loss on the test. And so at the end, you can even extract the cross-validation data. So each model was fit on this degree 1, degree 2, degree 3, and had different losses. And you get the loss list, and you get the parameters. I think we can update this a bit, but none of these is a bona fide model because it was just trained on a fold, but you might still be interested in the information that is there. So there are several ways to do these splits. We support several, like k-fold, leave p out, bootstrap, Monte Carlo. We're going to add more possibly, and I didn't put it here, but you can even use scaled if you want to reserve like a fixed 20% of your data, for example, for validation. Now, given that the model is a function, how do you do inference? Well, we are kickstarting this new ModelFit report object, and this is going to grow considerably. But right now, this is taking the role that was the inference part of fitted model. So this is the property bag. Yeah, you fit, and you see that, for example, the best model that we found was degree 2. We give you a bunch of information, give you the residuals. This model is a bit small, sorry, but this is the residual plot. This is a 1D model, so this is a trend plot. Is sorted by independent variable value. You have a probability plot, the residual histogram, but you can use it like any property bag. Yeah, you can get AIC, BIC, the training loss. You can do properties, of course. and see that what we do have. And I mean, here you have all the properties that you can get from the model itself, and all the properties that need the report because they need all the, like for example, quantile plot, which is a different form of the probability plot that that need the extra data that the report is holding. The model being like a function is a bit more lightweight. It doesn't carry all the residuals, doesn't carry the data. The report is what you want to go to if you care about the full inference machinery. And you can look a bit about model selection, like the candidate was model 2, and you have the loss distribution, you have model 3, and model 1 was the worst, was degree 1. And so this is telling you a bit like, this was selected through cross-validation using this method, and the criterion that we pick, we used to pick the best model was the root mean square error. And you can pass your own criterion, and this thing will also be greatly expanded in 15.1. Now, if you use a bit more like different model types, this becomes a bit more interesting. So we can still use our family of polynomials, but then we can use, for example, a k nearest neighbor with k1 through 5 in steps of 2, and the decision tree, which by default has all the, this goes to the default parameters, but you can customize, for example, the minimal gain per split, the tree depth, the minimal number of samples on the leaves, the minimal number of samples to consider a split, like is all customizable. And at that point, you can, besides cross-validation data, you can get the cross-validation chart, which is grouped by model type. And you see that, for example, like the tree was so-so, nearest neighbors as well. The polynomial was the best one, but the degree one was actually worse than other kind of piecewise. No, this was piecewise constant, and this was like a very local model. I see a question from Paul. Well, Fourier analysis, we do have a Fourier model that does Fourier analysis. So you can, I think it's called periodic model right now, and you can write. It's basically, one advantage of the framework is the modularity. We have a generic linear model, a generic formula model, and we have specialized models, for example, for exponential growth, power laws, periodic fitting. And what's the advantage? I mean, one of the main downside of using fine fit or nonlinear model fit is that they are very general. They cannot possibly know about your assumptions. Yeah, you have to bake in things. They cannot help you with smart guesses on the initial values. Yeah, for example, what periodic model is doing is it knows that you are fitting a bunch of sine cosines, so it can help picking the right starting values for the frequencies, for example. And we do that. We do a search, and of course you can provide your own values, but we can help you more there. Yeah, or the exponential model can try to get the right sign for the exponential coefficients, or the amplitude sign can estimate the baseline because it knows what an exponential is. Yeah, it knows like that there are certain things that you can rely upon. Sorry. So yeah, and then so this is basically the idea. Like every model is its own little word, and it's not just an equation. It's also a set of kind of properties that both you as a user and we as developer can rely on. So this brings me to the model zoo. So basically the idea is that we have basically two large families, like symbolic models, which have expression-like structure, and they boil down eventually to something linear or non-linear. You can have, the polynomial. You can have like something that I didn't manage to publish for 15, which was called actually Fourier model, which is basically fitting Fourier series, while the periodic model is a fully non-linear model where you can fit amplitude, frequency, and phase, exponential, power, and more. And then you have completely opaque models, or like not complete, like different degrees of opaqueness. That basically everything that doesn't boil down to an equation with parameters, like trees, nearest function, neural nets. We have perception model, which is meant to be kind of, we do have a neural network framework, but this means to be a nice entry point. And there are other things that why you want to use this, probably other a neural network for regression specifically, or classification. Now a little bit of the, kind of a bigger world where we are and the plan. So symbolic models, they essentially boil down to one big equation, which is, stuff that you can map to an additive predictor. You have your response variable is modeled, it is a distribution with some error model, which typically is Gaussian, but doesn't need to be. And it depends on parameters. And the parameters depend on not linear, because not everything here is linear, but let's say additive predictors. In full generality, you also have this trick of adding a nonlinear function to map some simple nonlinearities. So this is a big equation, but it boils down to stuff that you probably know. The simplest is a linear model, which we currently support right now. And now, linear model, the predictor has a simple shape, a constant, and a linear combination of features. So this is what is called the design matrix at each point, or design vector at each point. And these are the coefficients that you want to estimate. Now, we just managed to put this in because we are working on the plumbing, the whole model framework itself, beside the individual models. But we already are at a good point, and I see all these coming from in 15.1. Generalized linear, which adds a nonlinear transformation, G if it is here, and G minus 1 if it is here. Additive model that has a bunch of smooth terms like splines, or like you can use, in my prototype, you can use splines, you can use local model, which is basically Lewis, polynomials. Mixed model, very important when you have hierarchical data sets, or depend on you are sampling specific classes, for example. So you add random effects and you penalize least square. And then you have the final equation, which is a full family of generalized additive mixed models, the GAMM. So we plan to cover all of this, basically. Beyond symbolic trunk, you have, right now we have decision trees, neural networks, nearest neighbors. More to come, local model. We have like local model fit. We're going to refold it in the framework. Kernel models, Gaussian processes. I think I missed one update on this slide, like new things that will become, like basically you want to extract all the methods from predict and classify and make them like inspectable, like more transparent functions. So imagine like naive Bayes. Of course, once we have GLM, we add multinomial loss or logistic regression. Is all the things that you know and love, let's say, are going to make their way to this framework eventually. Now, one advantage compared to the old framework: very flexible data. You can pass just responses. You can pass like a bunch of like a design matrix style plus the responses. You can use arrow syntax. If you have your data separate, you can use all the inputs and all the outputs. If you want to quickly fit one column of a matrix, you can specify, like basically the default input when you pass something like this is matrix goes to -1. But you can pick the column if you need to fit the first column. You don't need to massage the data yourself. This is actually fully built on Tabular internally. So Tabular is a prime input form, and you can pick the name of a tabular column. You can slice a tabular by naming columns. You're gonna have some input and an output, and then you can group them. So eventually you're gonna support multivariate output, maybe in a couple of versions. And you can use TimeSeries, of course. Data types. So we spent a lot of time trying to make it very seamless. So we have a big canonicalization step at the beginning. So if you fit with quantities, we're gonna store it, and we're gonna give you an equation that is actually stripping units where it makes sense and reapplying them, so you don't have to do it manually. Date object, time object, This is working natively with strings, nominal and ordinal, Boolean. Like one advantage of building on Tabular is that we finally have types. So if you give me a column with strings, I can treat it as a categorical column, and solvers will not choke on it. There's a lot of work to be done here on feature extraction. That is going to be done, I guess, alongside the generalized linear and linear when we start supporting categorical input. Right now, we have a couple of models, KNN and trees, that can take categorical input and output, but this is going to grow. So yeah, I mean, the categorization is very useful to handle all this before fitting, before and after. So you just concentrate on picking the right model. Few things that didn't make it but are coming in the next version is support for weights, which is one of the major gaps with the old framework. And I regret not being able to add it in the first version, but yeah, we know it's missing and it's coming. And support for the year-round wrapper, which is strictly connected because you pass the uncertainty, and that typically becomes weighted fitting. Okay, let's dig a bit, if I have the time. I guess I have a little bit into these models. So the general structure for a model is hyperparameters, parameters, and variables. For a model without hyperparameters, you drop these two. You start with variables. This is why you can do power model X, for example. If you do have hyperparameters, this is optional, and also this is optional at the beginning. So you can do polynomial model too, and or you can use a full specification. Yeah, hyperparameters in full generality is an association. Like polynomial model is just degree, and you can spell it out if you want. But we offer a shortened syntax. Decision tree model has more. So if I do information hyperparameters, you see that you have a bunch here, and you can and by the way, you can set them, and you also can, if you use like an up to or a span syntax here, you can cross-validate on any of them. You can do arbitrary grid searches on this. So symbolic models in general, they don't need to be fit to evaluate. Yeah? So for example, this is a polynomial model of degree 3 in 2 variables, and I can just pass the 2 variables, and this will run. Sometimes you don't even need to specify the input size. We try to infer it. If you just want to play with it, you can just pass the input directly. So this is a log model on an input of size of dimension 2. Like a trained symbolic model, in the end, it just becomes just putting some values on the parameters. Yeah, if you do this is roughly equivalent of training. Yeah, like you fix the parameters, and this syntax basically means take the default value and assign the default name and assign values 3 and 2. So this thing here becomes this. One advantage of having symbolic models, I can do this. Yeah, I can do this, and now this model here, it remembers that parameters are A and B. Yeah, so something that we're working on is to integrate all these with D and integrate. Imagine doing sensitivity analysis. You don't need to decide between the the symbolic expression and the numeric expression, with the parameter substituted in, because you can carry both at the same time. This is another thing that I really like of this, and I want to push it forward as much as I can. Now, as I showed here, you can use this syntax to fix parameters, and this is kind of reducing the degree of freedom, and but it's tracking both basically. You can specify initial values, which is way more important for nonlinear model, of course, and everything is taken care of. So like this is a parameter value, this is a parameter initial value. So at the end, you're going to have the name, initial value, and value here. And we try to basically offer like different ways to specify things. Like one thing you can do, for example, here, sensitivity analysis, you define your function that is fitting depending on a variable and predicts at input value 40. And then here you can do a table, you can do a minimize, and you can reason about these parameters. This is like kind of a bit more cumbersome in the classical system because, for example, for linear model, you need to manually remove the variable and adjust the design metrics and things like that. So it's a bit more clumsy in the old framework. Okay, what's next? So I have a bit of time to answer questions. Oops, sorry. More families. I kind of mentioned several of them, but yeah, we're gonna grow this a lot. Complete feature parity with the old frameworks. Like variance. I don't remember how it's called. This option to specify the variance, estimator function, the weights, working precision and tolerance, where the optimizer supports it. Like all of this. This honestly is already done. It's just that I'm just waiting for the next release to ship it. Confidence prediction bands at any points, both symbolic, fully symbolic as equations if you have a symbolic model, and computed if you have like any model. So neural network is going to come with predicted systemic variance, aleatoric variance, decision trees, nearest neighbors, like everything will basically share the same system. These are what I call the runtime properties or evaluation properties, which is similar to what classifier function and predictor function are doing. Yeah, if you put a number in, and you can ask for like a round value instead of just the mean, or you can ask for log probabilities for the probability margin, like in a classifier. Extensive categorical support. This is something that is very large, and we really didn't have time to wrap it up for the first version. Now we do have ordinal as data type, so ordinal regression can be a thing here. And bonus point, you have time, like smart hyperparameter sampling. You could have not just grid search, but you could have like random search, like Bayesian optimization, some parameters. There's a lot of things you can do here. Okay, so we are basically at the end. So thank you for bearing with me here. Let's see about the questions. Now, let's see. New functionalities for statistical inference aim at fitting parameters of general ODE models. Well, funny you ask. I mean, right now, what you can do is you can use what is called, let's see if I can get out of full screen easily here. You can use here parametric and dissolve, parametric and dissolve value. There it is. So this allows you to fit, let's make it a bit bigger, to fit a differential equation that depends on a parameter. Yeah, and you can put this in formula model, for example, and
Sorry,
so,
Julio.
Yep.
Sorry to interrupt. We are seeing at your what's next slide. We are not seeing what you are showing in your screen.
Ooh, okay. I guess let me share the full screen then. Share screen. The entire screen. Do you see it now?
Yes, yes.
Okay, so you can put a thing like this.
Yes, sorry again, one more time. It's a bit small. Could you please go full screen?
Yeah, I'll go 200 or 300. Yes.
That's better.
You can do a thing like this, and this will take a differential equation and solve it depending on a parameter, and then you can pass the parameter and use a formula model to optimize it. That's fine. But if you can wait a bit, I have almost wrapped up a model that takes the differential equation directly, and not just that, also difference equation. So And it will come with the same machinery of the rest, like fixing the parameters, initial values, error bands, and everything. So yeah, all of this is totally coming to the framework. Now, does periodic model actually return constituents? Periodic model is, let me bring up the documentation page here. Periodic model has a model like this. Yeah, you decide how many frequencies you want, and it's fitting an equation like this. And you can extract, of course, the equation and everything. And as I said before, it has like some smart initialization. And yeah, I mean, I didn't write this one myself, so I'm not so familiar with internals. But you can pick on the frequency in terms of hyperparameters, and you can decide how much not really time but space to allocate for the initial probing. And just to show some examples, let me scroll down to some fit. Yeah, okay, here. For example, this is just an not really fitted, but is a a fixed periodic model with a variety of parameters, and but you can fit, for example, here. So this, you see, this is a periodic model of one frequency fitting on temperatures, and yeah. Now, beyond ordinary least square, what about linear fits from a sim linear of a form data error? Okay, so this thing here will be handled once we add a round support. You pass your data this way, around xi sigma I. So this is error on x, and same thing for error on y. Like, it's not really, I mean, while it's quite obvious what you do when you have errors on y, you basically do a weighted regression. There's not like a strong consensus on what to do here. I also would be curious to know, I think Eric was asking the question, if you have a specific algorithm in mind when you're thinking about error on the independent variables. For when we implemented this support for linear, nonlinear model fit, we use Fasano-Vio algorithm of like, is an iterative scheme where you basically move the uncertainty from x to y until convergence. But yeah, I mean, there are several ways to deal with this. Now, heteroscedasticity. Well, this is if you use something like, for example, you fit a perceptron that takes care of that. But we're gonna offer like more models that are heteroscedastic in the future, beside ordinary least square. Influence points. I confess I didn't think about that. I need to see how we can place it in the framework. Outliers, we do have transform anomalies if you want to remove them, but you probably are thinking of weighted regression here. So I think you could handle that with weights. It would be how can I do max? I guess. Yeah. Oh, I kicked one out, but I'm gonna answer this. Well, ARMA, and etc. When I have my current prototype is called the dynamical system model, and kind of I realized that it's kind of complementary to ARMA and friends, because in that framework you are typically more interested in modeling the noise. What our model is doing is basically the same equation, same math, but you care more about the like tracking the process and the process parameters. So I hope I can offer like a complementary view of that. Now the ones that I publish that I probably is down here. This one here, I did to max. Okay. Bayesian statistic functions. Yes, I guess. The point is, I want to wrap up feature parity with the old fitted model framework first and add more, because for example, the old GLM didn't have like a multinomial link, for example, or ordinary regression. So I kind of want to finish all that, and that's probably going to take me the next version. And then after that, of course, sky is the limit, but something that I'm very interested in do the Bayesian version of like, not really all, but many of these models. Yeah. So yeah, this is something that we definitely want to tackle at some point. Probably it's going to take us a couple of versions to do it. Now, let's still see. Virus infections. Well, we can guess it depends on the data. I'm not super familiar with the data source. Oh, appendix internal. I didn't show that, but yeah, I can actually show it, given that people noticed. I can actually show it live. I added a bunch of things about kind of, like why, I mean, what we're trying to do with the framework, a link to the current functions, but most of all, how we deal with stuff internally is not a big secret. We have, this model object. You can expect it. It is basically the foundation for the report. It turns like a function into a property bag, and the way this is handled is that these each model is its own type, and they have inheritance. So this, in the current my current nightly version, this is a lot larger already in terms of types, because we have like more like symbolic as its own trunk with all the uncertainty measurements assigned to it. So the idea is that you don't have to redefine the wheel every time. So why I'm mentioning all this, because at some point, each one of these models is registered with the same registration framework. And I wanted it this way because at some point, when we stabilize the framework, I want to open it up and allow you to register your own model. Yeah, so you can specify your own optimizer, for example, and as long as you follow the contracts in terms of what you return, then you can get for free like all the machinery about parameters, data canonicalization, all the views. Once you specify, how to measure the variance and such, you can get for free error bands and such. So like all the intervals. So yeah, this is the idea, and we have like a way to inherit, to define the right properties, which is also quite interesting and allows you to write the stuff very quickly. So I just wrote a function that takes basically all the property definition that are functions, and it extracts all the dependencies. So you can see how, for example, like AIC is depending, this is a bit complicated, isn't depending, AIC corrected is depending on AIC, which is depending on, if we make this big, it's probably sum of squared, sum in here, which is hidden by other things. And we have, like the log livelihood, these are all the hyperparameters. And yeah, I mean, you can see how basically this stuff works. It's not a big secret. And again, a bit more about parameter and hyperparameter. That's it. Okay. I see there are no more new questions. And I think we are at, okay, we're way beyond the end. So if there's nothing more, I can hand over my screen.
Thank you, Giulio. Yeah, I'll just put up my my window here again so I can show you the upcoming sessions and our webinars. We hope you'll join us next week. We'll be covering new in visualization, graphs, geography, and astronomy. Thanks to everybody, to our presenters, to Giulio, Gosha, and Rob, and our behind-the-scenes staff for answering questions. There is a short survey that we'd really appreciate your responses to. It's linked above, and it will show up on your screen as you exit and we close today's session. Yep, thanks, Rob, for pushing that out. We'll also be sending you a link to the recording so you can revisit any topics that you need to. But thanks for your time, everybody. We hope to see you next Wednesday.
Jimmy, maybe one question. Do the
Yes.
people here have access to our emails? Or, I mean, I saw some interesting questions. If people have any follow-up or like comment.
I would recommend that the survey form, we do have an open field in that survey where they can add any questions that they were not able to ask today or that they
Oh,
can
great.
ask later. And they can also communicate with us at wolfram-u@wolfram.com, and we will be sure to share any open questions so we get answers for everyone. Thanks, Julio.
That's great, because I think we are growing this functionality for the users, and the more feedback, the more engagement, the better we can make it. So thanks a lot for this.
Excellent. All right, thanks everyone.